Welcome to 6.07. We're going to identify the effect on the graph of algebraic transformations of sinusoidal functions. A lot going on there. Here's the basic idea. When we looked at the graph of sine of x and cosine of x, we noticed that while they have the basic characteristic we're looking for, meaning that they're periodic, they repeat themselves, they didn't do a perfect job of modeling our Ferris wheel situation, right? There are still some things that we need to change about them. In other words, we need to be able to transform these sinusoidal functions in a way that allows us to model real-life situations. And so that's what we're going to be working on today. So what is the amplitude and period of the function given below? So I want you to try and answer this first without graphing, and then I want you to graph it and look at your graph to help justify your answer. So it's two-part. I know this can seem kind of tricky, but give it a little bit of time, use your unit circle, and I think you'll do just fine. Okay? And then we'll take a look at the answer in a few minutes, but I want you to really try it first on your own. All right, I bet that you were able to figure out the amplitude. Notice that the amplitude is the distance above the midline that it takes to get to the maximum point. So what you've got to do is you've got to think about what is your maximum point and what is your midline going to be. Well, all we need to know is how sine works. So as we go around our unit circle, where is sine going to be at its highest point? Well, sine is the y-coordinate, so it's going to be greatest at pi over 2, and that value is 1. So the biggest that sine can ever be is 1, and so the biggest that our function can ever be is 3 times 1, or 3. Similarly, the lowest it can ever be, the minimum, is going to be when sine is negative 1. So the smallest that our function can ever be, the minimum point, is going to be negative 3. What's in between 3 and negative 3 is the line y equals 0. So our amplitude is the line y equals 0. Okay, now, I hope that you gave the period some thought before graphing. It can be tricky, and so in order to explain how we'd figure out the period, it is going to be helpful to graph this function. So what I'm going to do is I'm going to quickly graph this function. And the way that I'm going to do it is I'm going to make a short little table. And you could do it without a table, but I find that that can be really helpful for us. All right. So notice here that on the graph I have x values that are counting by 1, 2, 3, 4, which is different than when we counted by things in terms of pi. And notice that in life, we usually don't count by pi. And so using our sinusoidal functions to graph real-world situations, it's going to be helpful to think of ways that it makes sense, when we're counting by 1, 2, 3, 4, or whatever it is. So notice here that in my argument, I have pi times x. So when I plug in an x value of 0, I have pi times 0, which is 0. The sine of 0 is, of course, 0, and so my initial point is at the origin. 0, 0. All right, now let's move on to 1. You might be skeptical about plugging in 1 for x, but let's just trust that we can, make some moves if we need to. And notice that we have this multiplication of pi over here, and so we should be okay. So we have 3 sine of pi times 1, which is just pi. Okay, well, what is sine of pi? Now I'm over here, the sine of pi is 0. So again, I have 0. And my new point is here. Okay. Interesting. What should happen to my sinusoidal function in between these 2 points? Pause the video for a second and think about what could happen. As we've seen before, sine is either going to loop upward, come down, or maybe perhaps it would loop downward and come up. But let's think about what should be happening. As sine travels from 0 to pi, the sine value increases at first and then decreases positively. So it should increase and decrease. Where will the maximum point be? Well, the maximum point is going to occur when we have pi over 2 as the argument. So what will the x value need to be so that we get pi over 2? Well, that shouldn't be too tricky to think about. If we have 1/2 as our x value, pi times 1/2 is going to be pi over 2. So the value that I want to plot in between here is when x is 1/2. There, and I'll write this in a different color so we can see, we'll have 3 sine of pi times 1/2, which is pi over 2, and that will equal, and think about it, sine of pi over 2 is 1, and 3 times 1 is 3. And so this maximum point is going to occur right here. Now, you probably see the pattern, and you could probably continue this out on your own without a table, but we'll just do one more point. So now let's plug in 2. 3 times sine of pi times 2, which is 2 pi. And the sine of 2 pi is 0, so this again is 0. But we know it doesn't just travel straight across. We know that sine, as it moves down, is going to go negative, hit its minimum, and then come back up to 0. Where is it going to hit its minimum? Well, in between 1 pi and 2 pi at 3/2 pi, or 1/2. 3 over 2. So now I'll have 3 sine of pi times 3 over 2, which is 3/2 pi, and that is going to be negative 3. And I can continue. Going as such, moving downward. All right, now with this graph, I can see the period much easier. Going from one maximum to its next maximum, this happened at 1/2, and the next maximum occurred at 2.5. So to go from 1/2 to 2.5 is a distance of 2, right? This would be 2.5 minus 0.5, and that is a distance of 2. So our period is 2 units. And this is very helpful, because imagine that we were sketching a model where we were counting by minutes here in our x value. And so this is time here, and we might have a situation where we want to make one full rotation every 2 minutes. And so this would be a full rotation every 2 minutes. And essentially, what we're looking for is what is the gap in our x values that will take us once around the unit circle. So notice if I started at x equals 0, I would be right here, because pi times 0 is 0. And when I got to an x value of 2, then I would have gone all the way around the circle, because then I would get to 2 pi, or once around the circle. And so the x value distance that it will take to go all the way around the circle is 2, right? It will take me 2x units to go around the circle. And I could see this by looking here. Here's where I am at 0. I go up, I'm still positive. I hit the midline again, then I go negative, and finally hit the midline again. So it takes me 2 units in the x direction to cover all the possible values. All right, that one was a little tricky, but now we're going to go to a couple that should be a little easier. So go ahead and graph both of these functions on the same graph. If you need to make a table, make a table, and see what you notice. I'll take a brief look at this, and I'll show you how to graph them. But I want you to try it first, because I think you'll notice something really cool. All right, so I've graphed sine of x here. And now, you should have been able to do this without making a table. And now let's graph cosine of x, this cosine of x minus pi over 2. Okay? So let's make a table here. And let's just plug in a couple of values. So we have 0. So first that's going to be cosine of 0 minus pi over 2. All right, well 0 minus pi over 2 is just negative pi over 2. And so negative pi over 2 is starting here. We rotate clockwise pi over 2, which is down here. And so cosine is 0. Okay, so there's my point. Now let's go to pi over 2. Cosine of pi over 2, which is x, minus pi over 2. Well, pi over 2 minus pi over 2, that's 0. Cosine of 0 is 1. Let's try pi. Cosine of pi minus pi over 2. Well, pi minus half of pi, this is pi over 2, right? You can do that off to the side if you don't believe me. And cosine of pi over 2 is 0. And in fact, if you were to continue, 3 pi over 2 cosine of 3 pi over 2 minus pi over 2, well, 3 pi minus pi is 2 pi. So this is 2 pi over 2, or pi, and cosine of pi is negative 1. And if I continue, turns out that I'd have the exact same graph as sine of x, which is really interesting, because remember, when we graphed sine of x and cosine of x, we saw that they weren't quite matched up. But what this tells you is something really interesting, which is that if you take cosine of x and you subtract away pi over 2 from its argument, you're going to get the exact same function as sine of x. In other words, we have an equation, which is that sine of x is equal to cosine of x minus pi over 2. Or in other words, if you have a cosine function and you subtract away pi over 2 from the x value, you have a sine function. And I'll show you why this makes sense. By subtracting pi over 2 from cosine, instead of starting here when x is 0, you're backing it up pi over 2 units. You're really starting your cosine graph when x is 0 at negative pi over 2. Here, cosine is 0, just what sine is when x is 0. And so as sine increases, cosine increases, and cosine goes to 1/2, and sine goes to 1/2. Keeps increasing, cosine goes to root 2 over 2, sine goes to root 2 over 2. Then cosine goes to root 3 over 2, and sine goes to root 3 over 2. Then cosine goes to 1, and sine goes to 1. By delaying it, by pushing it back, what's called a phase shift, we are taking our cosine function and sliding it so that it now matches up perfectly with our sine function. And this is what's called a phase shift. Okay. So now we've seen all of the different transformations that could possibly happen, with the exception maybe one or two that we'll see in the future. And so now we're ready to take a look at the general form of a sinusoidal function. All right, so here's the general form of a sinusoidal function. Remember that a sinusoidal function is any function that can be written in terms of the sine. And since cosine, as we just saw, this fact that if we take cosine and we subtract pi over 2, that is going to be equal to sine. That is something that we need to keep in mind. Since this is true, we could take any cosine function, and by subtracting pi over 2 from the x value, we will now have the same thing as a sine function. And so these are both sinusoidal functions because they can be written in terms of sine. Notice that we have these parameters here. Parameters are the constants that are going to be a part of our function that are going to transform them. And what I want you to do right now is I want you to think about which of these are going to change the midline, which will change the amplitude, which will change the period, and which will change what we just learned, which is the phase shift. So your homework, your problem for tonight is to look at these and think about what will changing the A value do to my midline, amplitude, period, or phase shift, if anything. Okay, so for each of these, go through and think about what are these going to affect for our sinusoidal function. Okay? And tomorrow we'll do a little bit of experimenting to see what, in fact, they change.